Hi everyone! In the previous video, you learned that it's very important to have unique IDs assigned to things that we care about, which can simplify data integration. In this video, we'll look at what we would need to do if we don't have the luxury of having IDs. In practice, many things in the world are not indexed by knowledge bases, such as the Google Knowledge Graph. For example, in academia, it's very common for multiple researchers to have the same name. Or to be even more confusing, one person can have multiple names. For example, while most people call me Polo Chow, Polo is in fact not my legal first name. My legal first name is Dun Horn, which has two words, and very often citations would abbreviate them as DH, or even just D. This means just me alone, I already have at least 4 name variations. How do we resolve all these variations? This is in fact a hard problem, commonly known as entity resolution. That is, to disambiguate variations of the same thing. Why is entity resolution so difficult? Let us understand this through doing some shopping. Imagine we want to buy an iPhone, and we are considering whether to buy it from Apple, Amazon, or eBay. If you buy directly from Apple, then it's quite straightforward. You first visit Apple's official homepage for the iPhone, then select the size that you want. Then you choose the wireless carrier, then color, and finally storage capacity. And that's it. Apple already has an ID in the form of a serial number for every combination of size, carrier, color, and capacity. In other words, there's nothing for you or for Apple to disambiguate. Now let's go to Amazon. There isn't a web page dedicated to the iPhone. So you will need to search for the phone that you want using its search box. In the search results, instead of seeing only one phone, you see multiple phones, and also some accessories like headphones and cases. The phones may be from the same or different sellers, most of the time from Amazon, but sometimes from other third-party sellers. The phones may vary in sizes, colors, and so on. If a phone seller is Amazon, usually Amazon has already associated that phone with the correct Apple serial number, and there should not be any ambiguity. But it may not be true for the phones from third-party sellers. Now, let's go to eBay. It's even more challenging to figure out exactly which phone you might want there. eBay has numerous sellers, selling anything you can imagine. What's more is that eBay is also an online auction, meaning you can find both auction listings and fixed-price listings of the phones that you are looking for. And if your phone is popular, you may find hundreds or even thousands of such listings, each with a different price and a different listing title. This means while eBay may get you great deals, say through their auctions, you may need to do a lot of disambiguation yourself. You can imagine that eBay would love to see all the listings of the same products nicely grouped by their same unique serial numbers, but that is not always possible. One reason is that sellers get to choose how they set the listing titles, and they may or may not adhere to eBay's suggestion to associate their phone listings with the official Apple serial numbers. Another reason is that some products are just so rare that no one has ever assigned them IDs. So what do we do then? We don't need to give up. There are tools we can use. Besides using OpenRefine, there are techniques from research you may want to consider. One such tool is called dedupe, originally developed at University of Maryland. Dedupe resolves ambiguity among potential duplicates by simultaneously considering those entities' attribute similarity and relational similarity. Here, in this screenshot of dedupe, we're looking at information about researchers in the Research Collaboration Network. Each node in this network is a researcher, and 2 researchers are connected by an edge if they have co-authored a paper together. In the Relational Context Viewer at the top right, dedupe shows the potential duplicate researchers in region 2 and region 4. Here we see there are 2 researchers, possibly referring to the same physical person, with almost identical names. The name in region 2 has a middle name, while the name in region 4 doesn't. Neighbors shared by both researchers are shown in region 3, and non-overlapping neighbors are shown in regions 1 and 5. This means if we see there are a lot of nodes in region 3, then the 2 names in region 2 and 4 are likely the same person, because it is not very likely for many people to have worked with 2 persons with the same name. To determine textual similarity between entities, dedup offers a number of string-based similarity measures, such as string added distance. To summarize, dedup helps user locate potential duplicates by comparing the entity's attribute values, such as their spelling and also their relations, to see how many neighbors that they share. In more detail, dedup allows the user to adjust how to balance between the two types of similarities using a weight constant, alpha. The overall similarity score for a pair of entities is then the sum of the weighted average of the attribute similarity score and the relational similarity score. One important point to note is that there are many similarity measures you could use, and often it's not easy to know which one to use unless you try them. The rule of thumb is that you may want to start with the more common measures and then proceed to the more complex ones if the simpler ones do not work well. For example, for numerical values, Euclidean distance is a popular first choice, since it's easier to interpret and has nice geometrical meaning. If you want to compare two sets of items and determine the extent of overlap as a similarity measure, then you want to try Jacquard similarity, or Jacquard index, which is defined as a number of elements shared divided by the total number of elements. In the example shown here, we have two sets S and T. Set S has 5 elements, and T has 6. They share 3 items, and there's a total of 8 unique items. So the Jacquard similarity is 3/8. A Jacquard similarity measure of 1 means complete overlap, and a Jacquard similarity measure of 0 means no overlap at all. If you want to compare two pieces of string, like Polo Chow and Polo Chen, you may want to try string added distance, which measures how many textual transformations you need to do to convert one string into the other. The transformations include adding a character, deleting a character, or replacing a character. The more transformations you need to do, the less similar your two strings are. As mentioned before, there are many more measures you may want to try. For example, in MATLAB alone, there are already tens of measures, so go try them out. To learn more about entity resolution, I highly recommend the excellent KDD 2013 tutorial by Lees and Ashwin. In this video, we have looked at entity resolution and discussed why it's an important but hard practical problem to solve. And we also mentioned the role of similarity measures that's central to entity resolution. And there are many measures that we may need to try to figure out which one may be the best for our tasks.